Next example, eliminate the parameters a and b from each of the following equation and find the corresponding partial differential equation. Is again of the same type problem. So the previous problems are of the same type, that is formation of differential equation, partial differential equation. But if we observe the previous problems, then the problems are of this type, that f of uv is equal to 0. So uh, and the another problems are z is equal to, if you observe this problem, z is equal to f of x y, and we have to eliminate this function f. We have to eliminate this function f, or some capital F or small f or phi, and we have to form the partial differential equation. This is the answer of the problem. So in this problem, we have to eliminate the constants, arbitrary parameters a and b. Okay, so z is equal to, we are given directly the function of xy, the value of the function of xy in terms of a and b. So we have to eliminate parameters a and b, constants a and b. So again, the procedure is same, that is differentiate with respect to x and y, and then from that two equations eliminate small a and small b. Okay, that constants, arbitrary constants. So z is equal to x plus a into y plus b. So we differentiate with respect to x and y. So dava z by dava x, derivative of z is dava z by dava x is small p, and is what, with respect to x derivative. So derivative of x is 1 and derivative of a is 0, and y plus b is constant. So y plus b is the derivative. Then dabba z by dabba y, then x plus a is constant and y plus b, the derivative of this bracket is 1. So x plus a into 1 means x plus a. So equation 2 and 3. So I have to eliminate a and b from equation number 1, 2 and 3. We have to eliminate a and b from 1, 2 and 3. And that is the, we have the value of x plus a as z by y and y plus b as z by x, substitute in this equation number 1. So we have z is equal to pq, that is substitute 2 and 3 in equation number 1. We have z is equal to pq, and this is the corresponding partial differential equation. That is, this is the corresponding partial differential equation whose solution is z is equal to x plus a into y plus b. This is the solution of this partial differential equation. The next problem, z is equal to a plus ax plus y bracket square plus b. Again, the same type problem, we have to eliminate the arbitrary constants a and b. So differentiate with respect to x. We have dabba z by dabba x is equal to, the derivative of this quantity is 2ax plus y into derivative of ax plus y is a. The derivative of ax is a and the derivative of y is 0. Derivative of b is again 0. This is equation number 2. Then dabba z by dabba x is means p, small p is equal to 2ax plus y into a. Then differentiate this equation number 1 with respect to y. We have dabba z by dabba y is equal to again 2 times ax plus y bracket raised to 1 into derivative of ax plus y with respect to y now. So ax derivative is 0 and derivative of y is 1, derivative of b is 1. So into 1, 2ax plus y into 1 plus 0. That is q is equal to 2ax plus y. Okay, this is equation 2. And we have to eliminate a and b from 1, 2 and 3, from equation 1, 2 and 3. So we have the value of x plus, we dividing 2 and 3, that is p by q. We have p by q is what? P by q is 2x plus y into a divided by 2x plus y. And then we have a is equal to p by q. So substitute a as p by q in the equation number 3. So we have q is equal to 2 a x, a value of a is p by q x plus y, and therefore we have q is equal to 2 by q p x plus qy, and then shift the q to LHS. So q square is equal to 2 in bracket px plus qy. This is the required partial differential equation. So here we have the values of a and we have to eliminate a and b from equation 1, 2 and 3. So either use all the 3 equations 1, 2 and 3, or just use equation number 2 and 3. Here we have the elimination of a and b from equation number 2 and 3. So next problem, z is equal to ax plus by. So how we eliminate a and b from equation number 1, 2, 3? That is adding 1, 2, 3, or add 1, 2 and 3, or subtract 2 and 3, divide 2 and 3, divide 1 and 2. So we can eliminate a and b from equation number 1, 2, 3. So same type problem, we have to eliminate a and b. Z is equal to ax plus by. So differentiate with respect to x and y. We have the very obvious answer. Dabba z by dabba x, that is p is equal to a, and dabba z by dabba y as b. And then if we substitute a and b in this equation number 1, that p and q. So z is equal to px plus qy is the solution of this problem. Next problem, x minus a bracket square plus y minus b bracket square plus z square is equal to 1. So differentiate with respect to x. So we have 2 times x minus a raised to 1 derivative of this quantity. Then derivative of y minus b bracket square with respect to x is 0. Derivative of z square is 2z dabba z by dabba x is equal to 0. Z is the function. We have to differentiate with respect to x. So 2z dabba z by dabba x is equal to 0. And that is, we have the answer cancel throughout a. So x minus a plus zp is equal to 0. This is equation number 2. And then again differentiate equation number with respect to y. So derivative of x minus a bracket square is 0. 2 times y minus b plus derivative of z square with respect to y is 2z dabba z by dabba y is equal to derivative of 1 is 0. And so we have y minus b plus zq is equal to 0, equation number 3. And then equation 1 becomes, equation 1 is x minus a bracket square. So value of x minus a is minus zp from equation number 2. And the value of y minus b is minus zq from equation number 3. So substitute these values of x minus a and y minus b in equation number 1. We have this minus zp bracket square plus minus zq bracket square plus z square is equal to 1. So z square p square plus z square q square plus z square is equal to 1. And if we take z square as common, then we have p square plus q square plus 1 is equal to 1. This is the required partial differential equation. Okay. So next problem is ax square plus by square plus z square is equal to 1. So differentiate with respect to x. So twice ax plus twice derivative of by square with respect to x is 0. Derivative of z square is 2z dabba z by dabba x is equal to 0. Cancel throughout 2, and then we have ax is equal to minus zp. Dabba z by dabba x is p. So this is equation number 2. And then differentiate 1 with respect to y. Then we have ax square derivative 0, 2by plus 2z dabba z by dabba y is equal to derivative of 1 is 0. Dabba z by dabba y is q, dividing throughout by 2, and then we have by is equal to minus z2. And substitute these values of ax and by in equation number 1 in order to eliminate a and b. So we have minus ax square. Ax square is what? Ax square means ax into x, and the value of ax is minus zp. So we have minus zpx. Again, by square is b into y into y, by into y, and the value of by is minus zqy plus z square is equal to 1. And then this is the required partial differential equation. Z is equal to x plus y plus f of xy. So I have to form the differential equation. That is, now we have to eliminate the function f. So with differentiate with respect to x, we have dabba z by dabba x is, or derivative of x is 1, derivative of y is 0, derivative of f xy, x into y is f dash x into y, into derivative of x into y with respect to x is y. That is p is equal to 1 plus y f dash x into y. And then differentiate with respect to y, we have dabba z by dabba y as q, and derivative of x is 0, derivative of y is 1, plus f of xy derivative is what? F dash x into y, into derivative of x into y is x with respect to y, is x, f dash x into y. And then multiply equation number this equation 2 by x and this equation 3 by y, and subtracting, we have px minus qy is equal to x minus y, there is x, here is y, and this term get cancelled 0. So x minus xp minus yq is equal to x into y is the required partial differential equation. So formation of differential equation, if there is function f, then eliminate that function f. Z is equal to x into y plus f of x square plus y square. So differentiate with respect to x and with respect to y, we have divided by x as p. Then here the derivative of with x into y is y. F dash x square plus y square into derivative of x square plus y square is 2x with respect to x. Similarly, differentiate this with respect to y. So divided by y, that is q is equal to x into y, derivative is x, and the derivative of this quantity is f dash x square plus y square into derivative of x square plus y square with respect to y is 2y. Then multiplying equation number 2 by y and 3 by x and subtracting, we get py minus qx is equal to y square minus x square, and this becomes 0. That f dash x square plus y square 2xy, f dash x square plus y square 2xy. So their subtraction is 0. So we have the final answer. Py minus qx is equal to y square minus x square is the required differential equation. Next problem is phi x plus y plus z comma x square plus y square minus z square is equal to 0. And we have to solve this problem. We have to form the partial differential equation. So we have to eliminate this function phi, and this is the problem of the type phi function of uv is equal to 0. F of uv is equal to 0. So we have the answer by using the procedure that y minus x plus p z plus y minus q x plus z is equal to 0. The next problem is again of the same type, phi x square plus y square plus z square comma z square minus 2xy. So this is the problem of the type f of uv is equal to 0, and so we have this answer. So if the problem is of the type f of uv is equal to 0, then this is the procedure. That is the formula for f of uv is equal to 0 is this, that p da by uv da by yz plus q da by uv da by zx is equal to da by uv da by xy. Denote that u and v, the function this z minus xy, and this is the problem of the type f of uv is equal to 0. So denote this function as u, this function as v. Find the values of all these three Jacobian and substitute the values. We have the final answer. Okay. So these two problems are for homework assignment. So solve this problem by using the method f of uv is equal to 0 equation for problem number 1 and 2. Their solutions are also given here. So this is the first topic, that formation of a differential equation. The next topic is Cauchy linear differential equation. Cauchy linear. So let phi of uv is equal to 0 be arbitrary function of u and v, and u and v are the functions of x, y, z, in which x and y are independent variable and z is the dependent variable, and z is the function of x and y, but x and y are independent variables. So this phi uv is equal to 0 is arbitrary function where u v are the function of x, y, z, and x and y are independent variable, z is dependent variable. Then the partial differential equation of the form capital P into small p plus capital Q into small q is equal to R. What are these capital P, Q, R? This capital P, Q, R are the functions of x, y, z, and small p and small q are what? This small p is da by z by da by x, and small q is what? Da by z by da by y. So the differential equation of this form Pp plus Qq is equal to R are called Cauchy linear partial differential equation or Cauchy linear differential equation. Okay. So this capital P, capital Q, and capital R are the functions of x, y, z. Okay, and small p and small q are what? Are the da by z by da by x, and q is what? Da by z by da by y. So this is the general form of the Cauchy linear differential equation. Then theorem is what? The general solution of partial differential equation Pp plus Qq is equal to R is f of uv is equal to 0. f of u is equal to 0, where u is what? X, function of x, y, z is equal to c1, v as a function of x, y, z is equal to c2. Form the solution of the equation dx by p, dy by q, dz by r. So we'll see the proof of this theorem in the next lecture. The general solution of the partial differential equation pp plus qq is equal to r is f of uv is equal to 0, where u x y z is equal to c1, v x y z is equal to c2. Form the solution of dx by p, dy by q, dz by r. So proof of this theorem, let pp plus qq is equal to r be the given differential equation. Obviously it is capital P, capital Q, capital R are the functions of x, y, z. Small p and small q are dava z by dava x and dava z by dava y. And then consider this equation dx by p, dy by q, dz by r. This capital P, capital Q and capital R as equation number 2. Since u x y z is equal to c1 is the solution of 2, we have du is equal to 0, and what is the complete derivative of u? Dava u by dava x dx plus dava u by dava y dy plus dava u by dava z dz is equal to 0. This is the complete derivative of u. Then from equation 2 we have dx by p, dy by q, dz by r is equal to, suppose k, then dx is capital Pk, dy is qk, and dz is rk. And therefore equation 3 becomes, substitute these values in equation 3, dx, dy and dz as pk, qk and rk. So we have this equation is equal to 0, and then dava u by dava x p, through cancel k, dava u by dava y q plus dava u by dava z r is equal to 0, suppose equation number 4. Similarly, we have vxyz is equal to c2 is the solution of equation number 2. We have dv is equal to 0, complete derivative dava v by dava x dx, dava v by dava y dy, dava v by dava z dz is equal to 0. Again substitute dx, dy, dz as pq, pk, qk and rk, and dividing throughout by k we have this dava u by dava x p, dava v by dava y q, dava v by dava z r is equal to, and this is equation number 5. And so solving 4 and 5 by Cramer's rule, we have capital P divided by dava u by dava y, dava u by dava z, dava v by dava y, dava v by dava z, and minus capital Q is equal to dava u by dava x, dava u by dava z, dava v by dava x, and dava v by dava z. And similarly R divided by determinant dava u by dava x, dava u by dava y, dava v by dava x, dava v by dava y. Okay, and that is P divided by the Jacobian dava uv dava yz is determinant P's, and minus q divided by this is the Jacobian dava uv dava xz, and this is the Jacobian dava uv dava xy. And then we have p divided by this, and absorb this negative side, so write in the place of dava xz as dava zx, r divided by dava uv dava xy is equal to, suppose k1, and then dava u by dava x dava y, that is compare the first and third ratio. We have dava u by dava uv dava yz is equal to p by k1. Similarly, dava uv dava zx is q by k1, and dava uv dava xy as r by k1. And we know that if f of uv is equal to 0, then if f of uv is the general solution of partial differential equation, then the partial differential equation is, if f of uv is the general solution of partial differential equation, then the corresponding partial differential equation is dava uv dava yz into p plus dava uv dava zxq is equal to dava uv dava xy. So in the previous topic, the theorem is what? F of uv is equal to 0 is the general solution of partial differential equation. Then the corresponding partial differential equation is this, and substitute this dava uv dava yz as p by k1, this is q by k1, and this is r by k1. And then after dividing, multiplying by k1, we have pp plus qq is equal to r. That is this is the required differential equation. That is f of uv is the solution of the differential equation PP plus QQ is equal to R. So theorem is what? The general solution of the partial differential equation PP plus QQ is f of uv is equal to 0, where u and v are the solutions of the differential equation dx by p dy by q dz by r. So in order to find the general solution of Cauchy linear differential equation, we have to find the two solutions of the differential equation of the form dx by p dy by q dz by r. So this is the previous topic, that f of uv is equal to 0 is a given function, given solution, then the corresponding partial differential equation is this. Just substitute the value of the three Jacobian, that p by k1, k1, q by k1, and r by k1. From this we have the answer, that pp plus qq is equal to r. This is the corresponding differential equation whose solution is f of uv is equal to 0. So we'll see the problems of the Cauchy linear in the next lecture.